Hello students, let us discuss something on the basics of set theory, which will be very important in solving many of the Olympiad problems. So there are lots of problems where the concepts of basic set theory are absolutely necessary. So that is why let us have a look at some basic concepts of set theory, which many of you might have done in your class 9th or 10th standard. So first of all, what is a set and how to visualize this? So for this, let us start with an example. Say consider the following box containing some objects, say letters, numbers and words. So this is a box which contains some objects A, then there is a word called sodium, then there is a number called 2, then there is a letter Z, there is a word called car. So we see that the letters A, Z belong to this box, the number 2 belongs to this box, the words sodium and car belong to this box. Okay, but it is clear that the letters B, C, D, or in general anything other than the letters A and Z do not belong to this box. Okay, and similarly it is also clear that anything other than A, Z, 2, sodium and car does not belong to this particular box. So this box can be regarded as a well-defined collection of objects. Okay, so this box contains some objects and we know what are the objects. So the term well-defined that I have just mentioned, this term well-defined that I have just mentioned, it means that given any object in the universe, we can definitely decide whether that object belongs to the collection or not. Okay, that is the meaning of the term well-defined. So in mathematics, we refer to such an object as a set. So the concept of sets is very fundamental in mathematics, something similar to the concept of points in geometry. Okay, so in most mathematical studies, a set is not rigorously defined, but it is just taken as a very basic concept that we agree upon. So for this course, we agree on the following concept. So what is that? In most books, you will find it written this way: a set is a well-defined collection of objects. So the term well-defined means that given any object in the universe, we can surely decide whether it belongs to the collection or not. If we can do that, then that particular collection is called a set. So for example, if we write something like A equal to 1, 2, 3 within second bracket, then it is the set of numbers containing the elements 1, 2 and 3. So 1, 2 and 3 are the elements which belong to the set A. Symbolically, we write it using this. 1 belongs to A. This symbol, it is the epsilon. It is a Greek symbol. And 1, 2 belong to A. 1, 2, 3 they also belong to A. So that way we write symbolically. Also for this particular set, 5, 6 and 7 do not belong to A. So we write it this way: 5, 6, 7 does not belong to or do not belong to A. Similarly, A doesn't belong to A. Say the word cat does not belong to A. The number does not belong to A, and so on. Okay, so what is the set A? The set A is the set which contains the numbers 1, 2 and 3. So we are very much sure that A contains only the elements 1, 2 and 3 and nothing else. So another example, say B equal to A, 1, X, 7.5, 8.12. So B is a set with 5 members. So what are the members? A, 1, X, 7.5 and 8.12. So here A, X belong to B, but Y does not belong to B. So Y is not an element inside this set. 7 is not an element inside this set. 7.5 is an element. Okay. So in both the above examples, we are sure about which elements belong to A and B and which elements do not belong to A and B. Okay. Now let us consider another collection C of all tall students who are enrolled in the certificate course of Initiation into Mathematics Olympiads at GC College. So is it a set? So let us see who are the tall students in our class. It's very difficult to decide, right? Because how do we decide which students are tall? Which students will be called tall? The concept of tall or the understanding of tall may be different for different person. So there is a lot of confusion as to which student will belong to this set. So the word tall is not an absolute thing. That is the problem. It is not an absolute thing. It's a relative thing. That is something that is clear only when compared. So for example, in India, the average height is around 5 feet or 5.5 feet. So somebody of height having 5.5 feet may be called tall in India, whereas in New Zealand, the same person will not be considered tall. He will be considered short there, because in New Zealand most of the people have height of around 6 feet or so. So tall is a very relative concept. So thus the collection C cannot be regarded as a set. We do not know which elements will belong to that collection. However, if we define C as the set of those students in the course whose height is greater than 5.5 feet, then the collection C is well defined. Okay, so given any student, we can just measure the height and decide whether he or she belongs to the set C or not. Okay, so in that case, C will be a set. Similarly, the collection of all beautiful objects is not a set. The collection of all good students in a class, that is also not a set, because we cannot determine who are good student, who are bad student. Okay, if we say something like collection of all students who scored more than 80% in the last examination, okay, then in that case it becomes a set, because there is a specific criterion. Okay, so there are some notations which will be used regularly. Usually sets will be denoted using uppercase letters, that is capital letters like A, B, capital X, Y, etc. And elements of sets will be denoted by lowercase letters or small letters, small x, small y, small a, small b, etc. So if X belongs to the set A, we will write X belongs to A. Symbolically, we will write it this way. If X does not belong to A, we will write X does not belong to A, right? This symbol. So in writing or listing the elements of a set, the order or arrangement of its elements are not important. Okay, so 1, 2, 3, the collection of 1, 2, 3, collection of 2, 3, 1, collection of 1, 3, 2, they all represent the same set. Okay, so what is a subset of a set? If every element of a set A also belongs to another set B, then we say that A is a subset of B, and we write this notation as A subset of B. Okay, or we write it the other way, B is a superset of A. So for example, A equal to 1, 2, 3 and B is the set 1, 2, 3 together with 4, 5. That means B contains every element of A, right? Every element of A is also an element of B, so A is a subset of B. Okay, but the other way it is not true. B is not a subset of A, because the element 4, it is an element in B, but it is not inside A. Similarly, C equal to 1, A, 2, B, 3, C. It is also a subset, superset of A. Okay, or A is a subset of C, because every element of A is also inside C. But if D equal to say 1, 2, 5, 7, 9, then A is not a subset of D. Because why? Because the element 3 of A does not belong to D. Okay, so let us see how we justify this. A will be a subset of D only when every element of A is also in B. Okay, but here we see that the element 3 is an element of A, but it is not an element of D. That means there exists at least one element inside A which is not there in D. That means A cannot be a subset of D. Okay, so this logical understanding are very important in set theory. Okay, under what condition A is not a subset of D? This very simple concept will be absolutely necessary in all other future discussion on set theory. A is not a subset of D means that there exists an element X inside A which is not there in D. Okay, so yeah, so the opposite of or the negation of for every is there exists. Every element is there in B. The negation will be there is an element which is not there in B. Okay, So proper subset, A is said to be a proper subset of B if A is a subset of B and B has at least one element that is not there in A. Okay, so B has something more, right? So A equal to 1, 2, 3 is a proper subset of B equal to 1, 2, 3, 4, 5. Okay, so here you can see A is a subset of B, but B has some more elements than A. Then A is said to be a proper subset. So however, A equal to 1, 2, 3 is not a proper subset of the set B equal to 2, 3, 1. Okay, we have already seen B equal to 2, 3, 1 is the same set as A. So every element of A is in B and B has no element that does not belong to A. Okay, so that is why A is not a proper subset of B in this case. So if A is a proper subset of B, then we write in symbols as Y is a subset of B, or we use this symbol. So under what condition two sets will be said to be equal? Two sets A and B are said to be equal if they contain the same elements, exactly the same elements. That is, every element of A is in B and every element of B is in A. Okay, if both these conditions are satisfied, only then we say that the sets are equal. So in order to prove that A is equal to B for two sets, we have to prove that A is a subset of B, that is every element of A is in B. Also we have to prove that every element of B is also in A. Okay, so these two things we have to prove. This is a very fundamental concept of set theory. To prove the equality of sets, this is the only possible way we can prove two sets are equal. Okay. We have to show each is a subset of the other, right? So two sets A and B will be unequal. So under what condition they will be unequal? If we can find at least one element in A which is not there in B, or we can find at least one element Y in B which is not there in A. Okay, so two sets will be unequal if we can find such elements. So there are several ways of two ways of writing sets. One is the roster form or listing form. The way of writing a set by listing its elements explicitly is called the roster form of writing. So we just list the elements. A equal to 1, 2, 3, 4. It is the set which contains the elements 1, 2, 3, 4. B equal to 0, 1, 2, 3 up to 100. Okay, so this is the set which contains all the numbers from whole numbers from 0 to 100. Okay, set builder form is the way of writing a set by specifying a property that determines the elements of the set. Say the set that we had written earlier, A equal to set of 1, 2, 3. The same set can be written in this way. It is the collection of all those x where x is a natural number and x is less than or equal to 4. Okay, so we know what are the natural numbers. We assume we know is the set builder form of A equal to 1, 2, 3, 4. So here what is n? N is the set of natural numbers, that is counting numbers 1, 2, 3, 4, 5, 6, the list goes on. So A is the set of all those natural numbers which are less than or equal to 4. Okay, so then B also can be written in set builder form in this way. B equal to set of all those x such that x is a integer and x lies between 0 and 100. Okay, so it is the set builder form of writing this set, the same set. So here Z is the set of integers. So in general a set is written in set builder form and it looks like this: x, the set of all x such that Px is satisfied. That means where Px is a property that is satisfied by any member of the set. So some special sets that will be used regularly in our course are the set of natural numbers, the numbers that we use for counting 1, 2, 3, 4, 5, 6. You keep on adding 1, you get new numbers. The set of all integers, the positive and negative natural numbers including the number 0. So 0 plus minus 1 plus minus 2 plus minus 3, that way the list goes on. So these are all infinite sets. There are infinitely many elements. Means the list will never end. Okay. So and Q is the set of all rational numbers. Rational numbers means it is the collection of all numbers which are of the form P divided by Q, where P and Q are integers and the denominator Q is non-zero. Okay, so the collection of all such numbers is called the rational numbers. Okay, and any number which cannot be written in this form is called an irrational number. Okay, and if we take the collection of all rational as well as irrational numbers, we get what is called the set of real numbers. So the set of real numbers will be denoted by R. Okay, So any number that exists in our perception is a real number. Okay. So the concept of real numbers is actually a very wide topic in mathematics and forms the basis of the subject real analysis. So there are several ways or several important facts and rules that are associated with the set of real numbers. So as of now, we will just adopt the concept of real numbers in form of the number line. Okay. So the higher mathematics concepts of real numbers is not necessary as of now for us. So we will just take real numbers as being represented by the number line. So we have an infinite line and we mark a point 0, that is called the origin. So every distance will be measured from the point 0. So what is the real number x? If x is positive, it is the distance of 0 from the distance of the particular number from the origin. Okay. So if x is this number, x represents the distance from origin to this particular point. Okay. So a positive real number x is the point at a distance of x units from origin, okay, towards the right of origin. So if we travel towards the right, we get that is positive real numbers. Okay, if we travel towards the right of 0, we get positive real numbers. If we travel towards the left of 0, we get the negative real numbers. So it's minus x. Okay, so the negative real number minus x is the point at a distance x units from origin towards the left of 0. Okay, so each real number represents a unique point on this number line, and each point on this line represents a unique real number. Okay, that is how we assume this real number concept. So the set of real numbers contains all rational as well as irrational numbers, and we do not extend this discussion further as it is beyond the scope of our study as of now. And another concept that is quite important in set theory, that is the concept of empty set or the null set. Right? Consider the box described earlier at the beginning. So we have this box A, sodium 2, Z and car. What if this box is empty? Okay. Can we associate the empty box with a set? And the answer is yes. All we need to see that the empty box is a well-defined collection or not. Okay, can we say that the empty box or empty set collection of objects is a well-defined collection or not? So it's a quite simple observation. If it is an empty box, then given any object in the universe, we can definitely say that this object does not belong to this particular box because the box is empty, right? So if it is an empty box, then no object in the universe belongs to this box. So we are sure as to which elements belongs to the collection and which do not, right? That means we can consider it as a well-defined collection. Thus we have the concept of an empty set. A set that doesn't contain any elements is called an empty set or a null set. Okay, so if A is an empty set, then the statement x belongs to A is always false. Okay, if A is an empty set, then we cannot have any element which belongs to that set. So in many proofs we will see, we will encounter this type of statements. So when we encounter this type of statements for an empty set, we can conclude that there is some problem in our arguments. Okay, or we arrive at a contradiction, right? So it can be argued that now the question is whether all empty boxes are same, whether all empty sets are same. The answer is again yes. We have no other option. It can be argued that all empty sets are equal. So by definition of equality, we can make an argument. However, it is just trivially accepted. Every empty set is the same. There is only one and only one empty set. So for the sake of argument, let us go this way. The argument goes this way. Let A and B be two empty sets. Suppose A and B are two empty sets. If A and B are unequal, then by the definition of equality of sets, what happens? If A and B are unequal, then either there exists an element x inside A which does not belong to B, or there exists an x inside B which does not belong to A. But none of these are possible as A and B are empty sets, both empty sets. So we cannot show that, or we cannot argue that A is not equal to B. Okay. If A is not equal to B, we need to find at least one element inside A which is not there in B, or we need to find at least one element in B which is not there in A. Okay, but that is not possible. Nobody can find. That means we have to agree that the sets A and B are equal. So that is any two null sets are equal. Okay, so the empty set is thus universally denoted as the symbol phi. Okay, that is this is a Greek symbol, so it is denoted by phi. So some examples, let's see. The set A equal to the collection of all those x such that x is a natural number and x is strictly less than 1. That is the set of all natural numbers strictly less than 1. So it is an empty set as there is no natural number less than 1. Natural numbers start from 1 only. So 1, 2, 3, 4. There is no natural number which is less than 1. So that means this set has to be an empty set. The set B equal to x such that x belongs to real number and x square plus 1 is 0. This is also an empty set because there is no real number whose square is negative. Square of any real number is always positive, right? Or non-negative. So this set is also an empty set. So these are the very fundamental concepts of set theory. In the next video we will discuss some more concepts on set theory about union, intersection, difference of sets, and some properties of the union, the De Morgan's law, which will be very necessary, and some concept of the number of elements of a set. Okay, and probably something on Venn diagram, which will be very important for our understanding of set theory. Okay, thank you.